15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on Space Nuts, the Astronomy podcast. Episode 140. Starting to sound like one of those guys that calls the points on darts games. And my name's Andrew Dunkley, your host, and joining me as always is astronomer at large, Dr. Fred Watson. Hello, Fred.
Hi, Andrew. I'm wondering how Parallax is doing since we spoke last week.
I'm hesitant to check. I think my wife bought one.
Oh, good. That's good. No, you'll sell plenty of copies. Once the word
so.
sell. It's a good word, is Parallax as well.
Yeah, well, when I was trying to figure out a name for the book, I had that in mind. I thought, no, I'll just check and see if there are other books named Parallax. And I did a deep search, and I actually couldn't find any. I thought, you ripper. And then when I finally settled on it and everything was done, the cover was done, the book was uploaded, we were all ready to go, I did another search and I found 4. So
yeah. One of which is in my bookshelf, actually.
Yeah.
I wasn't going to tell you that.
So I don't know why I didn't find them the first time, but they're very different books. Mine's a science fiction novel. The others are rather different. And, it actually explains in the story why it's called Parallax. So that should, tease you into wanting to buy the book. I sound like you now. Yes.
You do, yeah.
Today we're going to talk about really fascinating stuff, including parallax. No, the Black Arrow projectile. This sounds rather intriguing, which we're going to look at today. The year of the periodic table. The periodic table's turned 150. It's the sesquicentenary of periodic tables, apparently. And somebody's written in, following up from our discussion about what is life. Remember, we talked about that a couple of weeks ago, and how do you define life, and what would you define life as if you found something a little bit different out there in the universe, like a talking rock? So we've had a question come back about the Drake equation, which is the equation that talks about the probability of life beyond our own planet, and there's been some movement in that area. So Mario from Melbourne's brought that up, so we'll tackle that one too. But first, the Black Arrow projectile. This is a really interesting little yarn.
Indeed, it is. It was more than a projectile. It was actually a launch vehicle. This was Britain's launch vehicle, developed during the 1960s. I remember when I was a lad, when I was leaving university and actually, thinking what I'd like to do with my career, because I absolutely wanted to be an astronomer, but there were other avenues that looked as though they might be related to that. And one of them was working for the company that was developing the Black Arrow, Hawker Siddeley Dynamics. And that was so when I was graduating from university and thinking about these things, it was very much on my horizon. Indeed, the Black Arrow project flourished. I think the program built 4 rockets between 1969 and 1971, of which the third flight was the first and actually only successful British orbital launch. I think it was Britain and a number of other countries as well, but Britain took the lead on that. So they actually put a satellite into orbit using the Black Arrow launch vehicle. And this really was the highlight of the Black Arrow program, because after that it was cancelled, presumably because of the sheer expense that's involved in developing these things. And by then there were competitors well established across the Atlantic from the United Kingdom. But that sort of, that short life has given it the Black Arrow rocket a kind of almost legendary status, and I kind of feel that as well because of my nearly getting involved with it when I was just leaving uni. So where did it make its flight? Well, it was here in Australia. Even though the Black Arrow was built in the UK, it was launched from the Woomera launch facility in South Australia. And basically put its satellite into orbit and then fell back to Earth and landed in the South Australian desert and has been there ever since. Until now, because this story is a rather nice sort of heritage type story involving I was going to say remnants. I think it's mostly in one piece, but it's very, very bent. Its various components have been seriously rearranged. The Black Arrow launch vehicle, but it has been brought back from Australia into the United Kingdom, and in fact. It is actually going, curiously, to a small town in Scotland where I used to live, a wee place by the name of Pennycook, not very far from Edinburgh. I lived in Pennycook for quite a number of years during the 1970s and 80s. So it's very nice to think that this piece of space history is going to be put on display, actually, in Pennycook.
All right. Now, the obvious question is why? Is it going to Pennycook?
Yes, I'm very, very glad you asked me that, Andrew.
I'm sure you would have told me without asking, but I need to feel useful.
Well, you just stick to your parallax, and I'll keep sticking to answers. It's because the company that's paid to bring it back actually is a high-tech company based in Pennycook. Its name is Skyrora. I think they do basically space-based industry, and so it's fantastic that this rocket vehicle is coming back there. The other really interesting aspect of this, though, is that Scotland might, in a few years, have its own launching site, bearing in mind that in the 1960s and 70s, British rockets had to be launched from Australia. Things have changed to the extent now that in far northern Scotland, you could actually have a viable launch site, particularly for north-south launches. That's to say, spacecraft going into what we call polar orbits. You tend to need a fairly clear eastern horizon, if I can put it that way, preferably with ocean there for normal satellite launches, but and you tend to want to be near the equator. Now, Scotland is not near the equator, but far northern Scotland will be a perfect location for polar launches, to put launches over the pole, and that is the usual kind of orbit that many military spacecraft are in, and also a lot of communication spacecraft too, such as the Iridium ones.
If they're going to start launching rockets from Scotland, they're going to have to really improve on their caber tossing, because seriously, that ain't going to do it.
Well, that's probably who they'll get to do it. Always, hey, we can throw a beam of wood, so we can launch a rocket.
Yeah. Maybe. It actually reminds me, and I'm glad they found it, and I'm glad they decided not to leave it in the middle of the desert rotting away and letting the vandals get to it, because I know they had a couple of cracks at it. But it reminds me of Australia's first attempt at a launch vehicle, which turned out to be a leftover American rocket.
It was, that's right.
Which we painted over with a kangaroo, and we launched it. And it came back down to Earth, and the paint half burnt off and revealed the American flag or the letters USA or something. And they shoved it in a chook pen. And it's still there to this day.
What else do you do with one of these? Yeah, you and I spoke about that a few...
We're so classy in this country.
It launched, if I remember rightly, was it RESAT? WRESAT?
Something like that, yeah.
Yep. Weapons Research Establishment satellite. Yeah, very interesting stuff. Well, there you go. So what delights me, Andrew, about this is that the space age has its own history. And I've seen most of it as well. I certainly remember the first
Sputnik. I didn't
Sputnik.
mean to laugh, Fred.
No, it's true. It's great to see to be able to see at first hand this progression of the technology from these first attempts like the Black Arrow and things of that sort to what we see now with SpaceX sending launch vehicles back up and landing them back on Earth on their tails and things of that sort. It's brilliant stuff.
At least the English one had a good name.
It's about all it had.
Yeah. But it is fascinating history, and I'm glad it's found a new home. It certainly beats being put in a chain mesh fence enclosure.
With chooks.
With chooks, probably, indeed. You're listening to Space Nuts, Andrew Dunkley and Fred Watson.
Roger, you're allowed through here also.
Space Nuts.
Now, Fred, to a topic that everybody knows from their childhood and going to school. I remember my science class, they had a periodic table on the wall. I didn't have a clue what it was about. And of course, it's an interesting thing, the periodic table, because it's changed many times over the years, and it keeps having new elements added to it as they are discovered. And I think as recently as 2013, it changed again, if I'm right.
2015.
2015. I knew it was fairly recent.
Yep.
But its original form was first put together 150 years ago. It's celebrating its sesquicentenary. Indeed
it is. And that's why 2019 has been designated as the International Year of the Periodic Table.
You know, when they started having international years of, I thought they really ran out of juice on the International Year of the Cane Toad. But every year I think, what's it going to be this year? This one's not a bad one. I think this is a good one.
I think it's a pretty good one too.
Because when you think about it, everything that we are made of is on this chart.
Indeed, that's right. And so it is, it draws attention to something that's fundamental. And the reason why we're talking about it in an astronomy podcast, of course, is that that periodic table of the elements, of which we now know, I think the number is 118, they would be the same throughout the universe. We've known that since the days of a man called Huggins. He was the British astronomer who figured out that the raw materials of the stars are the same as the raw materials on Earth. So William Huggins, he later became. I think that was actually round about the same time as the periodic table was put together in 1869. I'll come back to Huggins again in a minute because the periodic table has played this really important role in astronomy. So who invented the periodic table? Well, I'm sure you know, Andrew, it was a Russian scientist by the name of Dmitry Mendeleev. And he essentially took the characteristics of the known elements, of which, by the way, there were 63 in his time.
I actually do know a little bit about it because I did this as a radio question a few months ago. And so I'd done a fair bit of research on it. That's why I knew it had constantly changed over many years.
That's right.
Sometimes I actually know what I'm saying.
No, well, you do. You probably know more about this than me. Maybe I should ask the
question.
questions.
No.
So what Mendeleev did was he kind of arranged them by their atomic mass, which was something that was already known in the science of chemistry. So it's that kind of thing was cutting edge stuff to realize that different atoms weigh different amounts, and then the additional factor that came into this that really makes the periodic table what we know it today is something called the atomic number, which is the number of protons it has in its nucleus. And so actually today's periodic table is arranged by atomic number rather than atomic mass, or the mass of the elements. And now we kind of understand what that's all about. But Mendeleev didn't. But his genius was to realize that there were kind of repeating patterns in these numbers and in the characteristics of the elements. And that's what makes the what you might call the horizontal aspect of the periodic table. Sorry, the vertical aspect of the periodic table. I didn't do chemistry at a very high level, so that's why this is all exciting and new to me. The periodicity, the sort of the fact that some of these properties repeat, is why it's called the periodic table. And I think at the moment we have just completed the 7th period of the periodic table, and we'll probably get into the 8th period. But some scientists say, well, that's unlikely ever to be finished because there's not enough elements that are known. And then you get into really interesting areas like the stability of the elements. There are things called islands of stability in the periodic table, where you've got elements that aren't, for example, that aren't radioactive. Many elements decay very, very quickly into something else, so they don't last long. But on an island of stability, these things are rather long-lasting.
Yeah, you talked about how brilliant Mendeleev was in creating the periodic table and the way he did it. The other thing I remember from my research that I thought was astounding about the man was that he realised he could not have found it all. And he left.
Yes, that's right.
He left spaces.
He did,
for people
yeah.
to fill in later. I thought that was amazing.
He did, and that kind of connects with it takes us back to the astronomy stuff here, because William Huggins, who I mentioned, he was the first person to turn a spectroscope, namely a device with a prism, onto the stars and see what happened when you looked at the spectrum of a star. And he saw this barcode of information, which he quickly connected with work that had been done a little bit earlier by 2 German scientists called Kirchhoff and Bunsen, of Bunsen-Burner fame, of course. They had worked out that each element has its own kind of signature in the spectrum. What Huggins did, yes, he ran amok on the sky with his spectrograph and started classifying stars by their different spectral appearance. But he also found glowing clouds of gas, we call them nebulae, and he could see what we now call emission lines. These are bright spectrum lines. The spectrum is, instead of being a continuous thing from red to violet with dark lines across it put there by the elements, what you've got is blackness with a few bright lines in the right positions. And this is what the elements do when they start glowing. If you, for example, excite hydrogen with a current, it will give this series of what are called emission lines, these bright spectrum lines, beautiful to look at because they're all different colors. But the astronomers of the time realized that when they looked at these nebulae, these clouds of gas, there was no known element on Earth that corresponded to the colors that they were seeing. And in fact, they invented a new one. They called it nebulium. They assumed there must be something out there called nebulium, but they couldn't find any evidence of it on Earth. And it was a bit bizarre because it seemed to be as common as anything throughout space, but rare on the Earth. And in fact, one of the things that told them round about the turn of the 20th century that they were barking up the wrong tree was that there was nowhere on the periodic table for nebulium to fit in. They'd already looked at the periodic table, and what gaps there were didn't match the expected characteristics of nebulium at all. It's a bit reminiscent, Andrew, of the dark matter search that we're in the middle of now, because we know what we think this stuff should be like. The nebulium thing turned out to be, as I said, they were barking up the wrong tree. And it was in 1928, if I remember rightly, that a scientist, a very bright American scientist called Ira Bowen, realized that you weren't seeing the spectrum of an unknown gas. You were seeing the spectrum of something we knew very well, which was oxygen, but under completely different conditions from what we see it on Earth. And that's because it is in the near vacuum of space. Space has very, very low pressures, and even when you've got a nebula of gas in space, it's kind of 1 atom per cubic centimetre, rather than the kind of pressures that we see on Earth. And that was how the whole thing was understood. But the periodic table played its part in that.
Yeah, and I know I don't mean to be rude, but I think if you were to ask just about anybody of a non-scientific background to name 5 elements, they'd struggle. Maybe they'd come up with 5, but I doubt they'd come up with 10. But you could just name almost anything in a basic form and you'd be right. You know, lead, copper, aluminium, hydrogen, nitrogen, oxygen, barium. Don't really like the taste of that stuff. And, you know, potassium. There's just so many that everybody knows by name in everyday life, and yet if you ask them to list these things from the periodic table, they'd go, don't know. It's just one of those things. We all know it, but we don't.
So in a few decades, when parallax has become a world bestseller, we'll be talking about Dunkleum. Because Dunkleum will be a new, decidedly unstable chemical element.
Yes, you never know. And that sort of brings that element, boom, boom, into play in the fact that they have there still may be things to discover.
Oh, absolutely, that's right. Just a few. There are still things to discover. But happy birthday to the periodic table. I think it celebrates its 150th anniversary in March, so we'll look forward to that.
Indeed. The year of the periodic table. You're listening to Space Nuts. Andrew Dunkley here and Fred Watson there.
0G, and I feel fine.
Space Nuts.
Okay, we're back from our periodic break, and it's time to wrap things up with a question from the audience. And we say hello to Mario in Melbourne, who has pondered on a question following our discussion on what is life the other day. And he classifies himself as a nutter, Fred, which is really good. So there's more than 2 of us now. Hello, fellow nutters, he says. Love the podcast. Keep up the great work. Heard your podcast today re alien abduction, life, biology, evolutionary chances or changes in conditions, and life outside Earth, which reminded me about the Drake equation. What are the latest views and solutions on the Drake equation? Keen to hear the latest thoughts, as many of the equation's factors have changed over the past number of years, particularly, for example, planetary system-related numbers. Many thanks, Mario from Melbourne. It's a great question, and he's right. Things have changed pretty dramatically in recent times because of our capacity to discover things that are different out there. And, you know, we talked about what is life and the alien abduction theory, and we've had some interesting conversations about it in recent times, Fred. And he does bring up a good point. Where does this leave the Drake equation? I suppose you better firstly explain what the Drake equation is to remind us all.
Yeah, I was going to do that because...
I knew you would.
Well, you know, it's nice to just take the time to talk about the Drake equation and actually what it is and why it was set up. It was written down by an astronomer called Frank Drake. He wrote it down as a way of quantifying the number of possible civilizations within our galaxy, but he didn't actually, that wasn't his main purpose, if I can put it that way. His main purpose was to get people talking about it, about the idea, scientists in particular, about the idea of extraterrestrial life, what you'd need to find it, how rare might it be, is it worth looking? And apparently it was on the eve of the very first scientific meeting of astronomers who were involved with the search for extraterrestrial intelligence, what we now call SETI. So it was a great piece of thinking, and it still bears up pretty well today. So let me just explain what it is. It is a pretty simple equation. At one end of it is something that says n equals, and n is the symbol for the number of civilizations in our own galaxy, that's where we are at the moment, with which communication might be possible. In other words, they are sort of within the sphere of receivability, if I can put it that way, of signals to and from ourselves, rather than some civilization that went extinct billions of years ago. Yeah. So n is a number of civilizations, and then after the equal sign, there are 7 factors, and these are all simply multiplied together to give you an answer, the answer being the number of civilizations. So what are the factors? Well, I'll go through them because we've got time to do that. There is the average rate of star formation in our galaxy. In other words, the rate at which stars are being born. That's a fairly well-known quantity. It's one of these numbers that actually has a kind of hand-waving answer, but it's based on our observations of other galaxies. So we do have an idea of that, and it's about one per year. In fact, it's probably one per year. In fact, it's probably the lower limit of that. It was one per year, I think, was Frank Drake's estimate back in 1961. We now have a rather better idea of it. So a lot depends on the brightness of the star. There's kind of, there are things that you can twist in this, or tweak, should I say. But the standard rate of star formation today is about 1.5 to 3 stars per year, something like that. Next thing is the fraction of those stars that have planets. And of all the factors in the Drake equation, this is the one that we now know
it's changed
much more certainly, and it has absolutely changed. It's probably 1. In other words, every star has at least 1 planet, and that's something 20 years ago we simply did not know that. And I think astronomers 20 years ago would have thought that was rather more than they might have expected. Next is the average number of planets that can potentially support life per star that has planets. So here we're in, we're now in slightly vaguer territory, but from the Kepler data, there's something like, it could be 10% basically. Something of that sort. It might actually be a little bit more than that. We think from the Kepler data about extrasolar planets, there might be something like 40 billion Earth-sized planets in the habitable zones of stars a bit like the Sun. That's a lot. That's actually round about 10%. It depends how many you think there are in the galaxy, how many stars. We think round about 400 billion, 100 to 400 billion stars in the galaxy. So it's something between 10 and 40%. It's 4%, 4% and 10%, something like that. So really interesting stuff. Then there is this number, which is the fraction of those planets that might go on to support life. So the fraction of planets that could support life that actually develop life at some point. And this is where you really start getting into the hand-waving region. There are two schools of thought here, and you and I have spoken about this before, that many people think life is probably common. And in fact, if you look at simply the geology of the Earth, that suggests that fraction of planets might be quite a high one, and that may well be true if you're thinking only about microbial life, for example, single-celled organisms. We've had this discussion before that suggests that going on to multi-celled organisms might be the big sticking point, the bottleneck in the evolution of life. So if the fraction of the planets that could support life that actually do go on to support life is high, then the next one is the one that kind of brings it all crashing down a bit, because the next one is the fraction of planets with life that actually go on to develop intelligent life. And a lot of people now think that could be very low. That is really, it's a very difficult thing to estimate. Some people have suggested numbers which are much less than 1, tiny fractions of 1. A few people seem to think that complex life might be inevitable. I don't share that view. That would put that factor up to nearly 1. But actually, I think the opinion among astrobiologists is fairly broad, but I think generally speaking, it's pretty low. And then you've got the last but one, the fraction of the above which will reveal their existence via signals released into space, well, that could be quite high. We simply don't know the answer to that. I mean, we've released our signals into space willy-nilly since the beginning of the radio age. Whether anybody would pick that up is a different matter. And then finally, this is the crucial thing, because you might remember that we started off with a rate of star formation. In other words, this is things per year, things that are happening per year. So the final one is the length of time for which civilizations do release detectable signals into space. It's very hard to talk about this without people seeing it written down. But what you've got is this succession of numbers, some of which are quite small, some of which are very small indeed, some of which are large, like the fact that we know that the fraction of stars having planets is now probably 100%, so that's one. But who knows how long a civilization might reveal themselves by signals that are detectable in space. It depends. Some people have suggested less than 500 years for an earthly civilization. Some optimists think it's a lot higher than that. You can pay your money and take your choice. So you get a huge range of different answers for this. I guess the best answer that I've seen is maybe N is something around 10 million in our own galaxy. I'm actually, my own view is that is on the positive side, that it's actually likely to be much less than that.
Yeah.
It could even be less than one civilization that we could have. So the question was, what's all the new stuff that's gone into that? Well, it's the numbers themselves that have really changed. There are a few people who've tried to modify it with perhaps framing the question in a different way. Has intelligent life ever existed apart from ourselves? That might be another way in which you could put, you frame the numbers slightly differently. But the bottom line is it's still a very open question with really not that much improvement since Frank Drake did it, except that we now know that stars have planets.
Yes, indeed. And we're discovering more and more and more almost every day, and that changes the numbers. But as you and I have discussed many times, the probability of a life form with our level of intelligence or close to, that are capable as us technically, that are close enough for us to detect and ultimately return signals to, is almost nil. And as you and I discussed last week, the distance a radio signal travels in space before it's undetectable is 50 light years. So anything outside that range is pretty well going to be unknown to us. So it's a real needle in a massive haystack. And the probability of another life form equivalent to us existing in the same time frame is, beyond reasonable. And
on the other hand, Andrew, there was a piece of work that was done, I think you and I spoke about it at the end of last year, which, yes, it took all that on board, that maybe the statistics are very low, but it also made very clear that in terms of the kind of parameter space that we've explored so far, we've explored less than the equivalent of a bath full of water, a normal household bath in all the oceans of the Earth, when you compare it with the universe at large. So we're really only just getting our toe in the water, if I can put it that way. But I, for one, think it's still worth doing the analysis, keeping the search going. Wouldn't it be great to see another wow signal and have some follow-up? And
there are still questions and there are still unknowns, and as I have said many times, never say never.
Never say never, exactly. So the Drake equation is alive and well, still fairly depressing, but who knows?
Who knows, indeed.
We in the Space Nuts community we remain optimistic.
Yes, we do, as does Mario in Melbourne. Thank you, Mario, for your question. Greatly appreciated. It really does stir up some interesting discussion and debate. And thank you, Fred, as always. It's a great pleasure, and we'll catch you again real soon.
That sounds good to me. I'll look forward to speaking again, Andrew, and keep up the good work with Parallax.
Thank you, Fred. Fred Watson, astronomer at large, my partner in crime here on Space Nuts, and I look forward to your company next week.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.